Welcome. In this video, we're going to go through some Paper 1 and Paper 2 questions that will show up on the organic section of your IBSL test. So question number 1 here says, which three compounds can be considered to be a homologous series? So if I look at each one here and try and identify the functional group, I see an OH, an OH, and an OH. Here I see an OH, an HO, which is slightly different, and a COOH, OH, OH, and an OH, OH, O, and HO. So it's either A or C. The slight difference between A and C that makes A true homologous series is that in C, you notice that the OH here is going to be a secondary alcohol, whereas in A, those are all primary alcohols. So A would be the best choice. Question number 2 wants to know, what is the IUPAC name of the following compound? So if I look for my longest branch is going to be 4-carbon, either here, or I could, count that as my longest branch. But either way, it's 4-carbon. And then there's a side chain. So the side chain comes off here with the CH3 branch. So that is going to be considered 2-methyl butane, because there's a methyl group coming off the second carbon of 4, so 2-methyl butane. Question number 3 then says, what is the structural formula of 2,3-dibromo 3-methyl hexane? So I would start by drawing the hexane, so it's 6 carbons. You might as well draw them straight since you have the choice. The 3-methyl tells me that there's a CH3 group off the 3rd methyl, and the 2,3-dibromo tells me there's a bromine off of each of these. So as I write this from left to right, I would call it CH3, CHBr2, C, and then a lot of times I use parentheses to show the CH3 as a branch, CH2 2 times, and finally a CH3. So the one that best matches my answer is B. Number 4 says, which is the best definition of structural isomers? Compounds have atoms with the same atomic numbers but different mass numbers. That's not true. They have the same mass because you have the same kind of number of atoms. Compounds which have the same general formula but differ by a CH2 group, that's not true. They actually have the same molecular formulas, so neither of those are true. Compounds which have the same empirical formula but different molecular formulas, no, the whole idea is they have the same molecular formula. And D, compounds which have the same molecular formula but different arrangements. That's what we're talking about for a structural isomer. Number 5, which of the structures below is an aldehyde? And so as we look at these, the functional group OH indicates an alcohol. In O between here is either going to be an ether or ketone when we draw it out. The COOC is going to be an ester, and the HO here is going to be my aldehyde. So then if I scroll down to number 6 here, which reaction pathway describes how ethanol can be formed? So if I start with ethene and it undergoes addition to become chloroethane, that's possible because I could have the ethene plus HCl would give me a Cl and an H group there. So it'd be chloroethane. And then elimination or substitution could change that to OH, although it's called substitution rather than elimination, so I'm not sure about that name. Ethane could be substituted to get chloroethane, even though that's a complicated reaction mechanism. It does happen. And then chloroethane could undergo nucleophilic substitution to form ethanol, and that's more often what we call that reaction. So B's looking like a strong possibility. Ethene substitute to ethanol, no, that's addition when that happens. And ethane addition, no, ethane undergoes substitution. So these two have got the description reversed, so C and D are not. So B appears to be my best choice. A, they just got the name labeled wrong here. It should be a nucleophilic substitution. So number 7, we're going to eliminate, that's no longer required for IB. Number 8, which equations represent the incomplete combustion of methane? So incomplete means you're either going to form carbon monoxide or carbon instead of the CO2 and H2O. Along with that carbon product, you will still form water. So as I look at these, A is showing complete combustion, so that's not possible. Number 2 has got both products, CO and H2O, and number 3 has C and H2O. So both 2 and 3 work for incomplete combustion, so C would be my correct choice. Number 9 I put on just to remind you that you should be aware of some of the products we get from crude oil. So I want to know which ones are obtained from crude oil and are economically important. Plastics, definitely, that's what we do a lot of building of from crude oil. Margarine, not so much. That's usually alkenes being hydrogenated, so that's not coming directly from crude oil typically. And 3, motor fuel. So 1 and 3 would be my best choice. Common products from crude oil or fossil fuels, if you want to think of it that way. Number 10 then, what is the product of the following reaction? So what you should notice is that you've got H plus showing that you've got acidified dichromate. So these are the conditions for oxidizing an alcohol. And then I see the OH here, so I know it's a secondary alcohol. So I would expect to make a ketone or B here, CH3, CO, CH3, because this hydrogen and this hydrogen are going to produce H2 and leave behind the CH3, CO, CH3. Number 11, which compound forms when hydrogen bromide is added to butene 2? So I've got 4 carbons. Here's the center one. So when that opens up, when that bond breaks, I'm going to have a hydrogen here and a bromine here. So it is going to be 2-bromobutane would be the name of my product. It is not dibromo because it was HBr, not Br2. And it won't occur on the first one because the double bond was specifically stated as being between the second and third carbons. Number 12 asks, which substance is not produced during the combustion of alkanes? CO2 can be, CO can be with incomplete combustion, so can carbon. H2 will not be produced, so that would be my correct choice. H2O will be produced, but not H2. Number 13, what is the product of the oxidation of butanol 2? So I've got 4 carbons. It's an alcohol group on the second one. So if I oxidize this, it will remove this hydrogen and this hydrogen, leaving me with a ketone. And since a ketone has to be on an inner one, I don't need to designate this as 2-butanone. Simply butanone would be correct. Number 14, what organic product is formed in the following reaction? So I've got an acid, I've got the alkene here, I've got my catalyst, and I've got H2O. So when this bond opens up, I should have a hydrogen on one and an OH on the other, which means I'm going to be forming an alcohol. So if I look at my equation here, CH3CH2, it's going to form another CH2 right here, and then a CH group with the OH or the hydroxyl group attached to it, and then finally the CH2CH3. So A appears to be the best fit. Number 2 and 3, or B and C you can eliminate because there's no OH in B, and there's a sulfur that appeared in C. And then D, the double bond is inside here, so it cannot suddenly end up with the OH on the end. Number 15 asks, which structure could represent a repeating unit of a polymer formed from propane? I was a little surprised how many groups had trouble with this. I think B was a common wrong answer. It's a little bit tricky. Remember, propane means you have 3 carbons, and one of those sets of carbons has a double bond between it. So this double bond breaks, and it allows propane to add to each end. So now propane can add here, and it can add here. So to draw this, what we actually do is we draw it a little bit differently. We usually draw the double bond like this, and then show the CH3 off of one of those. So now when this double bond breaks, I get another C group with the CH3 hanging off of it. And over here, I get another propene. So it's actually CH2, CH3. So here's my CH2 group. Here's my CH group with the CH3 bonded to it. So A is the correct structure for the polymer with propene. Then moving into the paper 2 questions, number 16 wants to know what's the order of boiling points for these isomers of pentane, and most groups got the order in the correct direction. If they're 10, 28, and 36, then the long chain should be the 36, which is A. The one with the most branches, C, should boil the easiest at 10, and the 28 in between. And a lot of you made note of the fact that branches decrease the boiling point, but what you didn't tell me is why. And the because is an increase in surface area, which then increases the van der Waals forces. So if you'd mentioned either of those, the surface area or the van der Waals forces, I would have given you the second mark for the explanation. Stating the names, most of you had no trouble. With B, you've got 4 in a row is butane. We actually saw this on an earlier problem. You have a CH3 or a methyl group attached to it. That's the only place a methyl group can attach on butane is to the second one. If you include the 2, no harm, but not necessary either. The third one, you've got propane, and then you've got a methyl group off each side of the second carbon, so we would call that 2,2-dimethyl propane. Part B of this question, C5H12 and C5H11OH can both be used as fuels. Predict which compound would release a greater amount of heat per gram when it undergoes complete combustion. Suggest 2 reasons. It's going to be the C5H12. And some reasons why is because if you look at this, these are both forming CO2 and H2O. So if I look at the alcohol here, the pentanol, I already have an OH. I have the water, one water molecule partly formed. So I could have said because pentanol is partially oxidized, so it's one less bond that has to be made because I've already formed one of the hydrogen bonds. I could have made mention of the fact that the pentanol has a greater molar mass. And produces less CO2 and H2O gram for gram. Or I could have mentioned that the oxygen in C5 contributes nothing to energy. The O in pentanol doesn't change. Again, that hydrogen bond's already established, so no energy is going to be contributed from that bond. Or you could have made mention of the fact that you've got more CH bonds in there, which generally allows things to burn cleaner and release more energy. Number 17 wants to know, explain using equations the following steps in the free radical mechanism. And I told you I'd be okay with you just describing each step. So initiation, a couple key things you need to mention is that you need UV light, and it cleaves a halogen. More specifically, a halogen molecule. And it produces 2 free radicals. And the equation for that is Cl2, show the UV light, and then show the free radicals with that unpaired electron. Propagation, kind of a fine point that a number of you missed on this, is that it not only produces free radicals, but it consumes and produces a free radical. And that's what we call a chain reaction, when it sustains itself. An example of that would be when the Cl free radical hits a methane, a CH4, you end up with a CH3 becoming a free radical. The carbon now has an unpaired electron as that hydrogen pairs up with the other, with the chlorine and HCl. And then a second propagating one is when that CH3 group hits a chlorine molecule to become CH3Cl, but creates another Cl free radical. So those are two common propagation steps. And then termination, important to mention that two free radicals combine, and that ends the chain reaction. So a common terminating step is if 2Cl2, let me get this back for you, if two of the chlorine free radicals simply recombine to remake the halogen, or you could have two of the CH3 free radicals combine, get my dot over there, to form C2H6, a variety of different combinations, but it's two free radicals combining and ending the chain reaction. Number 18 asks about the polymerization of the alkenes, outlining two reasons why the polymers of the alkenes are of economic importance. So a lot of you told me what some of the different polymers were, but the focus here is what makes them economically important. And one is because there's no natural version of plastic available. A second is that they form very unreactive products, which can be good and bad, but plastic just does not break down. And then another thing that makes them economically important is the wide range of uses or properties that they have. And a third is that plastics are relatively cheap yet. Number 2 that wants to know, state the type of polymerization reaction shown by the alkene below. So it is combined to form all single bonds, so that lets me know that this was simply an addition. That's all they wanted to know. Was it addition, condensation, substitution? This was addition because it saturated the alkene. And then deduce the structure of the resulting polymer showing 3 repeating units. And this one you did better on than the propane one. A lot of you realize that this would be a C with a CH3 and a CH3, and then a C group here with its hydrogens. And this was the double bond, so that's going to open up here and allow another one of these units, the CH3, CH3, into C. And finally another CH3, CH3, into C. And it's important you always indicate that there's still an open bond at each end here. And it's an open bond, not a double bond, but there's still room for more to be added on. And then the last question asks, explain why monomers are often gas or volatile liquids, but polymers are solids. So it's worth 2 marks. A lot of you realize that monomers are smaller. So being smaller makes them lighter. And so smaller and lighter means easier to evaporate or vaporize, either one, because of less mass and less intermolecular force or van der Waals. So both of those contribute to monomers being more volatile.